Hello everyone, I'm Walt. I'm one of your SurfNav instructors, and today we're going to be showing you how to complete a Moonrise problem. We learned this in class. If you would like to learn how to do the fundamentals of celestial navigation, we can do that in class. In SurfNav here is for practice. So this is not a place where you can learn from scratch how to do celestial navigation. This video is meant to supplement what we learned in class, get you some practice before you hit the fleet. For this problem, we'll be figuring out what time the moon rose on May 3rd, 1981. You may ask why it's 1981. Well, our nautical almanacs are all copyrighted. There is a 1981 training nautical almanac that we'll use here. It is not copyrighted because it's used by merchant mariners to study for their exams. So the nautical almanac looks almost exactly the same in 1981 as it does today. The numbers are just different because it's a different year, but the setup is just the same. As always, if you are falling behind, feel free to pause the video or rewind or slow it down. Or if you're feeling really good about it, you can even change it to 1.25 or 1.5 times to get through it a little bit quicker. At SurfNav, we stress that there are many different ways to do celestial navigation. This is one way that we have come up with. We are going to use the SurfNav strip form in order to solve this problem. As always, it's up to you. As long as you get the right answer and show your work, you can do celestial navigation however you want. There's a lot of different ways to do celestial navigation. Let's get started. Let's take a look at our strip form. Here's our Moonrise Moonset strip form that we use at SurfNav. You'll see that it looks exactly the same as the one we use in class. We have the line numbers, the short step, and then the written out step as to what we should do. And then we have one column. In class, you'll see that we do have more than one column for those. Here, everything else is the same. We just have one column so that it doesn't take up the entire screen. This is the exact strip form that you'll be able to use on your SurfNav exams, as well as once you get to the fleet, we have Excel versions of all of these in case you want to make them your own. First off, let's zoom in so we can get a better look at this. The first thing that I prefer to do whenever I start a Moonrise Moonset problem is circle which one of these I'm doing. Is it Moonrise or Moonset? From the given information, we told you that it's Moonrise, so we'll circle that. There we go. We're doing a Moonrise problem. Okay, step one. Let's figure out the date and time of our first estimate. Moonrise and Moonset is a little different than sunrise sunset. It can happen at any time during the day. So we would take our dead reckoning position from where we think Moonrise is going to happen. And the date of that is 3 May 1981. Next up, step two, we'll take our position from where we think Moonrise would happen. That's the given information. And we told you that the position was 16 degrees, 42 minutes north, 133 degrees, 19 minutes west. Next up for step three, we need to figure out what dates we're going to use when we go into the nautical almanac. So for westerly longitude, which we're in, we're going to enter the day of observation and the following day. So the day of observation is 3 May 1981. And then the following day would be May 4th. Now remember, whenever we do celestial navigation, we always want a base, either a base latitude, a base time, or in this case, a base day. We want to remember that we are solving for 3 May, not 4 May. So a little trick I like to do is let's circle our base day so that we don't forget which one it is. There we go. We're going to need that later so we remember which day is our base day. Next up, step four. We need to figure out the base time. So on those days, what time is the moon going to rise based off of the central meridians? This is where we need to start by entering our nautical almanac. And here is our 1981 nautical almanac for training purposes only. You can see that here, as well as down here, and it's blue, just like the dummy rounds on our ship that we use from the 5-inch or the 30 millimeter gun. They're all blue. It's just for training, and it's not copyrighted, so we can use it to show you how to do celestial navigation problems and record them. Just the same. Here we go. Altitude correction tables. Then we have some more correction tables, the A4 table, and the nautical almanac. it's laid out the same way. So we're going to keep scrolling all the way down until we find 3 May. So we'll keep going. And here we are at May 1st, 2nd, and 3rd, which in 1981 were a Friday, Saturday, and Sunday. Let's zoom in a bit so we can take a look. As you can see, that's the same format as our current nautical almanacs from our current years. We have up here, this is our sunrise section, followed by our moonrise section over here. That's actually where we'll be today. As we scroll down, we see that we also have sunset down here, followed by moonset over here in the same location as our current nautical almanac. We'll scroll back up because we are going to be looking at moonrise over here, and we're going to zoom in so we can get a good look. Okay, so we're looking at moonrise over here. We have our latitude scale over here. So what we're looking for are 3 and 4 May. So these columns right here. And now what we want to do is make sure that we plug in our latitude as well. If our latitude is about 16 degrees north, we are between 10 degrees and 20 degrees north. So we're somewhere along here. For step 4, we're looking for our base times. That means based off our base latitude being the latitude that's closer to the equator. So since we're at 16 and we are between 10 and 20, the latitude that's close to the equator is 10 degrees. So that's our base latitude. So our base time for the 3rd of May is 0506 LMT, and on the 4th, it's 0559 LMT. That tells us that at every central meridian on the 3rd of May, the moon will rise at 0506 LMT, and on the 4th of May, it'll rise at 0559 LMT. So let's put that into the strip form. Here we are back at our strip form. So we're going to fill in our base times from the nautical almanac. Base times being 0506 LMT on the 3rd, 0559 LMT on the 4th. Next up is step 5, the tabulated interval. We need to find the difference between our tabulated latitudes, tabulated meaning from the table, from the nautical almanac. Let's go over to the nautical almanac to figure that out. Here we are back in our nautical almanac. I'm going to zoom in over here so that we can see the difference between our latitudes, our tabulated latitudes. So let's zoom in. All right, so what we're looking at is the difference between our tabulated latitudes. So for our latitudes, we're between 10 degrees north and 20 degrees north because we're at about 16 degrees north. So the difference between the tabulated latitudes is 10 degrees. 20 minus 10 is 10 degrees. So let's put that into our strip form. We're back at our strip form, and our tabulated latitude is 10 degrees. Next up, we have step 6, the time difference. We need to figure out the difference in time between the tabulated latitudes from our base going to the pole. So let's head back to the nautical almanac. Here we are back in our nautical almanac. We need to figure out the difference in time. So we're going to highlight our base latitude of 10 degrees north, the next one up of 20 degrees north. Now this is for sunrise. We need to move this box all the way over here to 3 and 4 May for moonrise. Watch me pan over. And here we go. So our base latitude for 10 degrees north on 3 May was 0506 LMT. For 4 May, it was 0559. We're looking for the difference in time from our base to the next number. So the difference in time from 0506 going towards 0501 is minus 5 minutes. So that's the difference in time for 3 May. For 4 May, going from 0559 to 0550, you need to subtract 9 minutes. So the difference in time for 4 May is minus 9 minutes. Back in our strip form, the difference in time for 3 May is 5 minutes, whereas the difference in time for 4 May is 9 minutes. That's going from the base, in this case 10 degrees north, to the next number, which is 20 degrees north. Next up, we have step 7, the latitude difference. The difference between our DR latitude, which is up here, and our base latitude, which is 10 degrees north. We can do a little bit of subtraction. If we take our DR latitude of 16 degrees 42 minutes north, and we subtract that from 10 degrees north, our base latitude, we get 6 degrees 42 minutes. Or if you want to change that into decimals, you'll take the 42 minutes divided by 60, and you will get 6.7 degrees. That tells us that we're 6.7 degrees from our base latitude. Next up, we have step 8. It's where we need to do a little bit of math. We need to figure out our correction. So what we're going to do is we're going to follow these steps. All of these numbers that are bold and in italics are step numbers. So we're going to take the latitude difference divided by the tabulated interval multiplied by the time difference to get our correction. In other words, we're going to take step 7, we're going to divide it by step 5, and then multiply it by step 6. So let's take step 7, which is 6.7 degrees, and in our calculator, we'll divide it by 10 degrees, and we get 0.67. We're then going to multiply that. Let's start with 3 May. Multiply that by -5, and we get -3.3 minutes. Don't forget that minus sign. That's important. We'll do the same for 4 May. We'll take 6.7 degrees divided by 10 degrees, get 0.67. That tells us that we're 67% of the way from 10 degrees to 20 degrees between our tabulated latitudes. Then we'll multiply that by the difference in time for 4 May, which is -9, and we get -6 minutes. The last step for this video is we're going to do step 9. We're going to take our base times and add the correction that we just figured out. So we're going to take step 4, which for 3 May is 0506 LMT, and we're going to add or subtract, in this case subtract, the correction of -3.3 minutes. So put that in our calculator, 6 minutes minus 3.3 minutes, and we get 0502.7 LMT. That's telling us that at every central meridian, if we're at our DR latitude of 16 degrees 42 minutes, then set for us at every central meridian at 0502.7 LMT. Let's do the same for 4 May. We're going to take our LMT of 0559, apply our correction of -6 minutes, and we get 0553 LMT. This is a good spot to, just so we remember which day is our base day, I like to circle the base day of 3 May, like this. That way, it helps me remember what number I'm going to use for my next step when I start figuring out what time the moon is going to rise based off of our longitude. Now, if this has made perfect sense to you, super, you can probably go on to the next video. For everyone else who might be a little hazy about the theory behind this, I'm now going to show you what all those numbers mean by putting it on a nice little slideshow so you can see visually where we're getting these numbers and what we're doing with them. This is what the theory looks like. So we've set up our north and south pole just like it is in the Nautical Almanac. We figured out that for 3 May and 4 May, we need to figure out the time in LMT that the moon will rise based off our latitude. This is the double interpolating part. It's not just a single interpolation like sunrise or set. We need to figure out 2 days. We've got 3 May and 4 Day. And let's circle our base day of 3 May. Next up, we need to figure out what our base latitude is. That's the one that's closest to the equator, in this case, 10 degrees north. At our base latitude, the moon will rise on 3 May at 0506 LMT and on 4 May at 0559 LMT. We also need to know, since we're not at 10 degrees north, we're about 16 degrees north, based off the Nautical Almanac, we are between 10 and 20 degrees north. So at 20 degrees north, 10 and 20 degrees north being our tabulated latitudes. At 20 degrees north, the moon is going to rise at 0501 on 3 May and 0550 on 4 May. What we need to do now is, well, we're somewhere in between there because we're at 16 degrees, 42 minutes north. We need to figure out what time the moon is going to rise on both of those days. What we did on this trip form is, okay, first of all, we figured out that between our base latitudes of 10 and 20 degrees, the difference in latitude is 10 degrees. We also figured out that the difference in time for 3 May between our base latitudes was minus 5 minutes, which is 0506 minus 0501. We got minus 5 minutes. For 4 May, we took 0559, and to get to 0550, we had to subtract 9 minutes. So that's where we got our tabulated latitudes and our difference in times. Next up, we need to figure out how far are we from our, so this is us up here, how far are we from that tabulated latitude? We did a little bit of math, figured out we're 6.7 degrees from our base latitude. Next up, we figured that we did a little bit of math on step 8. We took our difference in latitude, 6.7 degrees, divided it by our tabulated latitude, and got 0.67. So we're 67% of the way between 10 degrees north and 20 degrees north. So we're going to take 67% of the correction of time. In this case, the difference in time was minus 5 minutes. We took 0.67, multiplied by the difference in time of minus 5 minutes, and we got minus 3.3 minutes for 3 May. We did the same thing on 4 May, same difference in latitude, 6.7 degrees, divide that by 10, difference in latitudes, got 0.67, multiply that by the difference in time. In this case, for 4 May, it was minus 9 minutes, and we got minus 6 minutes for 4 May. We then applied that correction. So we took our base times, applied the correction, in this case for 3 May, minus 3.3 minutes, and we got a corrected LMT of 0502.7 LMT. So at every central meridian at our latitude of 16 degrees, 42 minutes north, the moon will rise on 3 May at 0502.7 LMT. We applied the correction on 4 May too, 0559 minus 6 minutes gives us 0553.0 LMT. What we're going to do in the next video is we're going to have to interpolate between these 2 days, figure out how far between the days we are, and then we'll continue on with the strip form as well. In the next video, we'll start with step 10, and when we continue on from there, that's when we double interpolate between the 2 days, and then do a little bit of arc to time to find out what time the moon is going to rise for us based off of our location.